Hey Dad, so I was going to totally send you this file, but I didn't want to have to render it and convert it to video, and I wanted to be able to explain a few things to you and control it. Anyway, so I put it all together in this. I downloaded this cool video blogging program that was free, which I don't know. If we ever end up doing the video blogging ideas, this will be cool, and it gives me a chance to test all that out. This is the little video blogging app. It's kind of cool. You can put like right now, all I'm doing is I'm recording my screen, and then I'm simultaneously recording up here my selfie laptop webcam at the same time. But this is for the freeze dryer, and I want to show you. I know I put it on your computer, this file, but I don't think you kept the program that you would need to look at it. So I designed this in Blender, which is a 3D animation software used for all kinds of things, and it's basically just a copy of a commercially produced freeze dryer with just a few things that I changed, things that are better than that one, because the corners that they cut to save on production. For example, they did not have the second cooling coil. They used the same one, which I didn't really like that idea. So it's pretty self-explanatory. It's kind of funky in the drawing because I have the refrigeration circuits set to be completely see-through. So you can see no matter how I swing this, the refrigeration circuits are always visible. So I have the thing. If you look down over here, over on this side, you can see I've got the chassis, I've got the cold trap, I've got the product refrigerator, I've got the product heater, and then I've got the vacuum system. So I've got them each kind of in their own little thing. So if I wanted to move them around, I could. Anyway, so it's pretty basic. You've got the big product chamber up here that you would insert things into, and then in this drawing I have the evaporators as the cooling racks. I think that'll end up being the best. I mean, you lose the ability to reposition the racks because obviously the evaporators are fixed by their pipes, but I feel like that's going to freeze stuff the fastest and keep it the coolest if we end up, and I think they're trying to come up with a blast freezer is probably just going to explode the costs and the difficulty. But even if you wanted to do a blast freezer, you could we could make that work here by just turning the entire product chamber into a wind tunnel, basically. I followed your advice, I think, just for simplicity and reliability, to not have the product refrigerator be a heat pump. I think because we're going to be running it for such long periods of time, and because it's going to be the bigger and the more important of the two, I think just having it be a fixed metering device, refrigeration system that we just rob out of some kind of a freezer and putting it in there. Heat strips are cheap enough and easy enough that I think that if we I've drawn it in here, see the red portions. If we just lay the heat strip material over the top of the evaporator coils, and then they can just work together. When one is off, then the other one can be turned on. I've got it drawn in here that the vacuum system pulls first through the cold trap and then up into the vacuum. See, get a good angle of that. So the vacuum pump here would pull through the cold trap, which would just be another. I would just use another tank. It also it's going to be under this. It's all going to be under the same exact vacuum pressure. So I think a round propane tank that you purchased, either just a regular 5-gallon propane tank, or maybe one of the tall boys that's the same diameter but a little bit taller. I think they're like 10 gallons ones, and then we just cut the end off, and drill a couple of holes and weld our pipes onto it. Vacuums, the way that they work, resistance, the friction along the tubing has a huge impact on retarding the strength of the vacuum. So if you want to pull down the pressure within the chamber itself quickly and effectively, the tubing that connects the chamber to the vacuum needs to be as short as possible, and it needs to be as big in diameter as possible. Small diameter tubing, just the resistance from the friction of the material moving down the smaller diameter tubing and the longer tubing will actually have a massive impact on on slowing down the process of vacuuming the system. In fact, in my drawing here, where I've got these two big long lengths right here and right here, that would not be desirable. We'd want to either move the pump closer or move the cool chamber back more in reality to keep these pipes literally as short as possible. Same thing with the height. You know, you'd want all of this to just be as short as possible. We have to have some amount of length because the vacuum has to pull through the cold trap before it gets to the chamber, so that it protects the vacuum. So we're going to have that, but the pressure won't all pull down equally. The piping closest to the vacuum pump will see a way deeper vacuum than the rest of the system, and it's just how fast can it pull material through all of that. And then obviously as the pressure drops, it becomes much more difficult to actually get the material up in the product chamber to actually move down the pipe. And as it does, all the resistance it encounters will actually hugely affect our ability to pull the vacuum. That being said, I was looking at the triple points, and I was looking at the pressures. We don't really need to or want to pull a huge vacuum. We want to pull deeper probably than Wayland's machine is, but it doesn't need to be crazy. So then the cold trap, I have it drawn real simply here, as just, the vacuum tube comes down into the center. That will force the material as it'll enter the trap up through here, and that'll force it to kind of mix around and move throughout the entire device before it actually goes down the tube. We'd probably want to reposition this, and in reality put the evaporator coil in front of this tube so that the material was forced to travel through the evaporator before it could even get down the pipe, increasing the chance that moisture will be captured. In this application, I do think that it would be beneficial for us, for the system to be a heat pump. So I drew a little reversing valve in there because art. So because this system is much more simplistic, and because it isn't going to be running, it'll run for long times as a refrigerator, but it wouldn't be running as a heat pump for very long. The reason why I decided that it wouldn't be beneficial to have the product refrigerator a heat pump is because the product refrigerator is going to end up needing to either run as a heat pump for extended period of times. I didn't understand how much heat we were going to want to put into the product system. I think it would be very hard with a heat pump to finely control the heat levels that we wanted to. The heat pump is going to generate way too much heat, so we'd be turning it on and off constantly, and probably just running it too much as a heat pump. And the refrigeration systems that we're going to be robbing out of these refrigerators, you can convert them into heat pumps, but they're not designed for that, and using them heavily as a heat pump you'll end up destroying them, or at least you won't get the results that we probably want. But this this refrigeration, the cold traps refrigerator, we're only going to run it as a heat pump just to melt the ice to speed, so that we don't have to wait for ice to melt. Literally, you turn it into the heat pump, turn it on, let the compressor crank around for a few minutes until it actually achieves pressure and movement of the refrigerant, and that coil is immediately going to heat up to 150, 160 degrees, and then you shut the whole thing off and just let the heat that it's generated melt the ice, and then you just put a little drain valve somewhere on that and you could drain the ice. If you put ball valves here and here that were refrigerant or that were vacuum tight, you could, in the middle of a session, if you were doing like soup or something that had a huge amount of moisture and you completely plugged up your evaporator with frost to the point to where it wasn't effectively working anymore, we could install vacuum tight valves here and here, and then isolate the pump and the product chamber, break the vacuum in the actually you'd only need to isolate the product chamber. The pump could be fine. So you isolate the product chamber, break the vacuum in the cold trap, melt the ice, drain the cold trap, and then start the vacuum again. You could also do that while the vacuum was actually running, but melting the ice while the vacuum is running would be stupid, because then you'll end up sucking up the vapor. You'll melt it into a liquid, but you'll end up with some vapor. You'll end up with some more moisture returned to the vacuum. So it'd be easier to shut the vacuum off, melt that, drain it, turn the refrigerator back on, get this frozen again, and then reestablish the vacuum. And you wouldn't be able to do that while the vacuum is running, because the drain system would have to be much more complex in order to not allow the vacuum to be broken. So that's stupid. Yeah. So if you put a valve here, you could shut the system off mid freeze dry, because the vacuum up here obviously as the product sublimates and the and off gases, the vacuum up here will constantly be rising, the pressure will constantly be rising, but you're only talking about a few minutes. So by the time you finish draining the trap and got the whole system back up, you probably wouldn't have lost a huge amount of vacuum, or at least not enough to have done the problem. So that's my little design. You can make it as big or as small as you want, but I think bigger is better for us. One of the advantages that we have over a commercially produced system is that scaling up isn't going to cost us anything. Mass producing units, unit after unit after unit, size and capacity have huge cost effects for companies like the Harvest Right. But for us, we're only buying one vacuum pump. We're only buying one product chamber cylinder. So scaling it up, how much more expensive is it going to be to create a vacuum tight tank that's 5 feet long as opposed to one that's only 2 feet long? It's really not going to change our costs a whole lot. Buying a quality vacuum pump, buying one that has higher capacity is only going to be a few $100s extra. It's a one-time purchase for us. So I think scaling it up and making it big, the time constraints on the system are going to exist no matter what we do. You're going to end up with fairly long processes. So I think increasing the size of each batch is going to greatly help us out. The other benefit is increasing the size of the chamber doesn't scale up the length of time or the difficulty to accomplish what we're doing. As long as we have a big enough vacuum pump to handle the size, you could still put a little batch in there and it will do the little batch that much faster. The capacity, the size of the chamber, having it big, assuming that you can pull it down to vacuum, it'll actually help us, because the small amount of gas that escapes, that sublimates out of our product, will be absorbed by the greater volume of the vacuum chamber. A tiny, tiny vacuum chamber really quickly can get overwhelmed, and then the pump gets overwhelmed not because the pump doesn't have the capacity, but because your little tiny chamber just pressurizes too quickly from the off-gassing. Faster I mentioned the tubing that the vacuum pump has to suck on. The vacuum pump can have all the capacity in the world, but if your chamber only holds, a few square inches and you're producing more than a few square inches of gas, then your vacuum pump is still going to lose the race. I was going to look at this. So this is just a triple point chart for water. So 1 bar is 1 atmosphere. The bar translation to microns or to the mTOR that you are using on the on Wayland's, it's about right here, that we would be operating between the 1 and the 10 on well, we would be operating between the 10 and the 100 U bars, but Wayland's is floating right around 1 millibar. So at atmospheric pressure, these are temperatures, obviously. So at atmospheric temperature, the boiling point of water is 100 degrees Celsius, and the freezing point of water is 0 degrees Celsius. The freezing point of water is pretty straightforward until you increase significantly in pressure, and then it gets stupid. We don't deal with that, so we don't care. We're all about down here. So the triple point is called the triple point because that is a single pressure / temperature in which water can exist both as a liquid, a solid, and a vapor. But what we're interested in is that if you go below the triple point, liquid is no longer possible, and the phase change for water can happen immediately from solid to vapor. And so as what we want to do is we want to make sure before we, up here at atmosphere, we want to make sure that we take the product, down so that we're well into the frozen. The entire thing has to be completely frozen throughout. So in order to ensure that, we need to be down around here. This chart isn't built for freeze drying, sorry. It was the only one I could find that had the temperatures and that had the temperature scale that wasn't in Kelvin, because I didn't want to bother trying to convert Kelvin. I'm not familiar enough with it, and I didn't want to have to do that much thinking. And then U bars was a pressure that we were more familiar with. The atmospheres over here, the bars convert more friendly to the units that we'll actually be using, which is the mTOR that you're measuring. That's just it's inches of mercury, but it's just in the metric system. It's millimeters of mercury, and then in order to make it more precise, it's been split up into smaller measurements. So the right here, the 1 bar would be 0 millimeters of mercury, and then as you go down, we'll be around like between 100 and 400 millimeters of mercury, or around 25 to 29 inches of mercury. Our machine will, I think, easily pull down the system down to almost the last few 100 microns before we get to absolute zero. I don't think I'll have any problem doing that. But I don't know, maybe we'll be off-gassing more than that. So I wanted to show you, so I was going to look at this. You already understand everything I just explained. I don't know why I rambled on for so long. We want to freeze the system, we want to freeze everything down to this temperature, and then we want to pull it down into a vacuum. But then once we get it down into the deeper vacuum, then you can start applying heat, and all you're doing is you're further encouraging, whatever is left as a solid to come out. And as you apply the energy, you allow the phase change to happen. You can, the heat provides the energy necessary for the phase change. Without the heat, you can't change phase. There's a decent amount of heat absorption that takes place. That the individual molecules have to absorb, and it's significant. These charts don't really go into the phase change really, but that it takes increasing the temperature of the frozen water takes a certain amount of energy. in order to increase the temperature 1 degree, it takes a certain number of BTUs. The last degree that you go through, where the phase change actually takes place, requires significantly more BTUs, because the phase change demands additional energy. So if so many BTUs per second were enough to have raised the temperature up to the boiling point, or in this case the sublimation point, we need I forget what it is, but there's an exponentially larger number of BTUs that are needed to actually jump us to that last degree and actually phase change. So by increasing the heat in the entire system, we make sure that there's ample energy, there's ample BTUs available to all of the solid food, all of the water molecules within the food, to encourage the phase change and to allow that to take place. I also want to show you this because this is how our controls are going to operate. I think it'd be very, very easy to do this manually, but if you wanted to, I also think it'd be very, very easy to create a very simple logic board that would just run 2 or 3 passes. I mean, it's only checking for a few things. It would say, am I below a certain both the temperature and the pressure gauges that we are going to be using resistance. They're going to be resistance-based sensors. So you would literally just tell the logic board, check this circuit. If I'm above or below a certain resistance, then pass and go on to the next, go to the next step. And then it would check for this other one. That would be the pressure check, right? So once it passes the pressure check, then it would check for the temperature. And then as long as it passed the temperature check, then it would go on to the next cycle. And so you could really easily have a very simple, single-use homemade circuit logic board that would be able to turn the vacuum, increase and decrease the vacuum, and increase or decrease the temperature in the system in order to maintain whatever set point that you were asking for. Or you could get one of those programmers that you were talking about, and you could program that. The programmer would give you the flexibility of, in the future, if you ever wanted to add something or change something, be very, very easy to do that. But I think you could make your own printed circuit board much, much cheaper, probably, than messing with the programmer. And you wouldn't have to teach yourself anything there, because it's all stuff that's already very familiar and very known. I also think, just doing it manually, you could literally just have a dial that you set pressure, and then have another dial that you set temperature, and those controls are incredibly cheap to purchase for refrigeration equipment, where it literally just says, over that set point, turn the air conditioner on. Under that set point, turn the heater on. Over that set point, turn the vacuum on. Under that set point, turn the vacuum off. And just set the 2 dials, till they line up where you want them on the chart, and let the thing go. I think doing that manually would be very, very easy. But that's how you could get the controls to work. Here's how the mTORs and the microns, which are the exact same numbers, just one is smaller than the other, and then the bars that we were talking about. So 1 atmosphere, which is this is sea level atmosphere right here, is 750 of your torrs, or 750,000 microns. In the refrigeration world, we're pulling down to around 100, between 100 and 500 microns is what we're looking at. What most freeze drying takes place at is between 40 and 400 microns. Torr, which is way, way higher than what we're doing in refrigeration. Yeah, so there's what I think we should do for the freeze dryer. It doesn't have to look like this, but I think that would be the easiest, simplest thing for us to do. I didn't draw any of the controls just because the controls are all just going to be whatever we decide that they're going to be. Most of the actual controls for the refrigeration systems are just going to be the controls that were pirated out of whatever freezers we cannibalized to make them. Yeah. Anyways, this was my first little video thing. It's a lot longer than it needed to be. I wonder if I should edit it. Maybe I should get a better microphone. That sounds really weird. Better lighting too, probably. Anyways, yeah. So, cool.